I'm very happy to introduce Colin Nuckolls, who's, as you heard, filling in for Alex Pines, but I'm sure will fill in a very admirable way. Colin is at Columbia University. He did his bachelor's degree in chemistry at the University of Texas, where he worked with Marianne Fox, his PhD at Columbia with Tom Katz, then a postdoc at Scripps, finishing in 2000. At which time he came back and joined the faculty at Columbia, where he is now. He has numerous awards, including the ACS Bakeland Award, the Arthur C. Cope Scholar Award, Sloan Fellowship, Beckman Young Investigator, and others. Professor Nuckolls' lab is interested in creating and synthesizing new types of molecules that assemble into functioning devices. The essential element of this program is a synthetic effort that allows the design, production of new structural types and assembly motifs. And once these things are synthesized, he investigates the molecular and macromolecular assembly characteristics of these systems, aiming for a deeper understanding of the interplay between molecular structure, assembly, and emergent function. His current research efforts are aimed at creating novel and general methods to assemble and interconnect organic structures into functioning molecular scale devices that are useful for energy transport and conversion. So I'd like to invite Colin up here for his talk on From Molecules to Materials.
Thanks a lot. I'd like to thank Mark for the invitation. He told me when he invited me, I was invited because I was almost a physical chemist. So, I guess that shows how far the apple has fallen from the tree. But I'd like to start off by first, saying congratulations to Professor Fox on winning the Medal of Science. I think that's really fantastic. And I'd also like to start off by saying that the award from the Dreyfus Foundation for me came at a time that it was not only the money, which was nice, but it was also the recognition that comes at a very important time in your career, and it was really instrumental for me in advancing to tenure and on up through the ranks at Columbia. And so I'd like to thank the Dreyfus Foundation, and I was honored when they called me yesterday to ask me if I would come and speak at this. So, What I put together in the intervening 12 hours was I decided I would try to talk about single molecule electrical devices that we were making, and there's basically two kind of short stories that I'm going to tell here. And in my group, we view this type of architecture where you have some sort of electrode material, a linker, which is termed X, some sort of molecule or nanostructure, another X, and another electrode that you could wire into a circuit, as being a really fertile area for discovery. And it's at the intersection between chemistry and engineering, physics, material science, and that's where we derive a lot of our excitement. And I was trained actually not as a physical chemist, but as an organic chemist or physical organic chemist. And so we are able to make things that oftentimes other people would not be able to make, and in collaboration with groups in our nanoscience center and elsewhere, we're able to actually attach electrodes and look at their properties. And I think these types of schemes are still largely unrealized, and they're also underexplored. And I think there's a lot of really interesting questions you can ask when you start thinking about this, about what type of contact, what that X should be in terms of having those contacts be as transparent as possible. Is it possible to design systems here that behave as highly conductive systems? And can we make molecular devices that do something other than just carry current? Because that's the task that has been embedded in all of our laptop computers and is the basis of the silicon industry. And you'd really like to use molecules for something other than just this sort of dumb task of carrying current and switching. And then obviously you can, when you start making cartoons like this, you begin to ask questions of how a single molecule would behave that would be different than an ensemble. And then I'll touch in the last half of the talk on ways in which we're starting to look at very high throughput and statistical approaches to realizing this cartoon and what we found in the process of doing that. And I think the key message here is that this is sort of set up to be the most, by definition, one of the most sensitive devices in the world, because it's, if you think about the current going through this molecule, it's like when many of you got on an airplane to come here, if the person in front of you is slow getting their bags into their overhead carrying bin, the person behind them is slowed down. So all of the current has to constrict through a single place, just as all of the passengers have to constrict through that very small aisle on the airplane. So they're inherently very sensitive. They're sensitive down to the single molecule level just by definition. And then on top of that, the electronics that are used to measure this is the same electronics that's the foundation of the silicon industry. And so you have basically the most ubiquitous measurement platform on the planet that also is likely to be able to be used almost anywhere as well. So those are some of the things that motivate us in this. And I think there's an interplay between reaction chemistry and electronics, and I think it happened over almost the same amount of time, where reaction chemistry developed the ability to go from making relatively rudimentary structures to nowadays, if you're willing to pour another can of postdoc onto a problem, there's nothing that you can't. If you draw a reasonable structure on a piece of paper, you can synthesize anything that you can draw a reasonable structure for. To also, on the flip side of that, what is developed in the electronics industry is something where the first transistor was about the size of an egg. Nowadays, where the feature sizes, the smallest feature sizes in my laptop are on the order of, say, 45 or 50 nanometers, and that's shrinking all the time. So I think there's a real interplay between this type of reaction chemistry and electrical materials. And obviously, to this group, which is a group of chemists, molecules bring a lot to the table. They bring diversity, recognition, switching, actuation. And then, as I mentioned, electronics brings these short length scales. And the silicon industry is, developed tools to work with a real diversity of materials. And so you have a real wealth of different types of materials that are essentially limitless, and the length scales are short. And so that also provides a very fun sort of sandbox, if you will, to go and play in. And so in this talk, I'm going to try to make structures like this and look at their properties. And let me just give you a little bit of background. There's, when you look at a cartoon like this, there's obviously a lot of things that you could begin to vary. You could look at different types of molecular bridges, different types of in-groups. And my group developed several years ago a method of actually taking metals that weren't gold surfaces, but ruthenium metal surfaces, which you can actually see the individual ruthenium sites in the STM microscope, and you could treat those with diazoalkanes. And this was obviously the intellectual touchstone for this was work that was done in the Grubbs group to make metathesis catalysts. And we wondered if these types of surfaces, if they were actually able to support these types of metal carbene linkages. And the reason we thought these were interesting is if you make computer models out of these, it looks like from the metal into the molecule you have a nice conduit to get charge. And so you should be able to make contacts that are transparent in the electronic sense. And so we treated these clean ruthenium surfaces with 4-bromo diazomethane, and what we found on the surface was that we could actually attach this 4-bromophenyl group, 4-bromophenylcarbene. And the interesting thing is that not only were these groups able to form monolayers on the surface, they were actually able to undergo a metathesis reaction with vinyl trimethylsilane, and we could actually watch this back and forth between going from this monolayer to that monolayer through this metathesis reaction, and we could do this on surfaces or in particles and grow polymers off of the surface. Another way you might envision actually putting reaction chemistry into electrical materials is by designing new types of molecular wire synthesis. And so a student in my group, Matt Carnes, decided he wanted to look at ring opening metathesis polymerization of things like dibenzocyclooctatetraene, with the idea being that if we appropriately functionalize the monomers, if we could make living polymers out of this, we could make graphene ribbons that would have the ends of them differentiatable because we were making these in a living sense. Turns out that dibenzocyclooctatetraene is a fantastically bad substrate for metathesis. But what Matt found was actually maybe even more interesting. He found that he could actually synthesize this molecule, which has one cis and one trans double bond in an 8-membered ring, and that molecule then turns out to be strained enough with the Grubbs first-generation catalyst to make living polymers of this kind of unusual structure that have an alternating cis and trans double bond along the polymer backbone. This monomer here is actually there's an interesting story behind that monomer in that Wittig of Wittig reaction fame had actually synthesized this molecule, and he mischaracterized it as the cis-cis compound. And it turned out Cope had actually made the cis-cis compound, and they argued in the literature as to why their two infrared spectra didn't agree, and it turns out ours agreed with Wittig's, and so we managed to resolve a controversy that I don't think anyone actually knew existed except for possibly Wittig and Cope, who weren't here to tell about it. And along those same lines, Matt Carnes also synthesized this molecule that has one cis double bond and one alkyne, and that molecule is also very strained if you look at the crystal structure of that molecule. And he found that he could make polymer out of that by doing ring opening alkyne metathesis polymerization. But he found that the polydispersity was huge, which is characteristic of the other types of ring opening alkyne polymerization. And that led a postdoc in my group, Felix Fischer, to look at molecules like this. And what he found was that through a combination of a new catalyst and this modified substrate, he could make the first example of a ring opening alkyne polymerization that was actually living. And we think now we have derivatives of this that we can convert into these types of graphene ribbon structures through this type of polymerization. Another way you might imagine actually incorporating reaction chemistry into electrical materials or electrical devices is by making very small gaps and trying to do chemistry in those. And this shows the work primarily of a graduate student who's now at Berkeley doing a postdoc named Jinyao Tang. And what he came up with is he said, making small gaps is hard. What I'd like to do is actually come up with a way where I didn't have to do a lot of lithography. And so he'd put down a layer of platinum, put aluminum on top of that, and then he'd take it out into the air. And when he did, the aluminum would oxidize to aluminum oxide. And it would swell, and he could evaporate platinum and then strip off the aluminum and the aluminum oxide. And what you're left with are two platinum electrodes. And the interesting thing is that actually, because this is not done lithographically, a protrusion on one electrode seems to be mirrored by an indention on the other electrode. And so you can make very small, on the order of 3, 5, 10 nanometer gaps. Beyond that, this approach is not viable. And that allowed us to look at some in situ chemistry. And things like these terpyridyls, when they bind cobalt, we could see the device go from an open state to a closed on state. Or we could do imine condensations between monolayers that were terminated with aldehydes and bifunctional diamines, and we could bridge the ends of these, and we could see they could go from off to on. And in this case, we could actually reverse this and strip out the metal ions to make these things behave reversibly. And that got us to thinking about this original cartoon where he said, well, what we really need to do if we really want to make something that's a single molecule, because in these devices, this is a 3 nanometer gap, but this is on the order of 30 nanometers wide. And so you're going to have many molecules in parallel. The electrodes themselves have depth to them. And so you're looking at many molecules in parallel. So if you really wanted to realize this type of structure, the simple, sort of simple-minded approach to that would be just to thin down these metal wires to where they're about a nanometer in width and about a nanometer in height. There's a couple of problems with that, though. If you start thinking about this grain structure in the metal, if you make these lines very thin, that's not going to behave as a metal anymore. And then on top of that, there's an issue with these types of metal electrodes in that the molecule can bind to the top face of this electrode or the front face, and to a first approximation, the chemistry there is essentially all the same. So we wondered if there was a way that we could actually get away from having to make these types of metal electrodes. And that got us to thinking about, well, maybe single-walled carbon nanotubes, which have molecular dimensions in terms of their width. Maybe we could actually go in and do lithography on those and excise a section of those. And if we did that, we would then have a contact that would have two ends pointing at each other. And now the ends would be carboxylated, because during the lithography you would oxidize a section of this out. And even a bad organic chemist like me could make contact to carboxylic acids through amine couplings to make amides. And so we decided we would grow these individual single-walled carbon nanotubes using CVD. We'd put electrodes down on them, we'd characterize them, and then we try to develop the lithography to go in and cut them. And so working with Philip Kim and Jim Hone in physics and mechanical engineering, we developed a lithographic process that was at the limits of what you can do with electron beam lithography. Basically, we put in a layer of polymethyl methacrylate, and we open a window over the top of that is on the order of a few nanometers, and then we introduce an oxygen plasma, and we etch out a section of the carbon nanotube. And what you're left with then is this picture that I tried to paint in the previous slide, where you have these two ends of the nanotube which have carboxylic acids that are pointing at each other, and they're separated by the distance that you wrote into this device using the lithography. And so this shows one of the devices after it's been cut. And in our poor facilities at Columbia, our SEM doesn't have the resolution to actually see this few nanometer gap that we've cut into the carbon nanotube. If you're actually willing to do the needle in a haystack operation to scan across the surface of this many microns of carbon nanotube to find the few nanometer gap, you can do that. And the postdoc that was on this project at the time, Xiaofeng Guo, actually did that, and you can actually see that there's been a very small gap that's been cut out of this carbon nanotube. And so we can make many thousands of these devices on a chip, and we can then go in and try to do chemistry on the ends of these carbon nanotubes. And we optimized this process around a molecule that was 2 nanometers in length, and we would go in and we would perform this cutting, and then we would go back and take carbodiamide coupling reagents and pyridine, and we would try to connect them with molecules that had alternating single and double bonds. And I should say one thing, that the carbon nanotubes, when they're made, you get a distribution of the types of carbon nanotubes. So the diameter of them varies somewhat. That depends on the size of the catalyst particle. But then how that graphene sheet rolls up as the carbon nanotubes are made, not to imply that that's the mechanism, but if you think about this graphene sheet rolling up, how that sheet rolls up determines the band gap of the material. And so about 30% of the time you're going to get a metallic carbon nanotube, and about 70% of the time you're going to get a semiconducting carbon nanotube. And so we see both types. So this is showing the silicon wafer serves as a common backgate for all the devices, and we're looking at the drain current in the device as a function of the gate bias that you apply at a constant source drain voltage. And for a metallic carbon nanotube, you can't shut it off because it's a metal, and you see that the line is relatively flat. For a semiconducting device, you can see that you can turn it on and off. And after we go in and do this chemistry on Jennifer Claire's diamine molecule shown here, we see that the device recovers to a fraction of its original conductance. And we find that about 90% of the time the devices are open circuits, and about 10% of the time the devices recover to a fraction of their original conductance. And I'm always wrong when I make predictions to my students, and they know that by now. But I thought that what we were doing was that our gaps were the distribution, our gap size must have been larger than the molecular length. So I asked them to make a longer conjugated molecule. They made this molecule, which is now 6 nanometers long. We found that the yield dropped in half. And so the after-the-fact rationalization of that was that we had optimized this cutting process around a molecule that was on the order of 2 nanometers long, and now we had essentially overshot the gap, and so the yield of devices that actually recovered to a fraction of their conductance was cut in half. And I should also note this red line is after the cutting process. That's an easy way to tell that you've actually cut the tube, because these things go down to the noise level of the measurement. And that's why this red line looks so flat, is because it's many orders of magnitude lower in terms of the amount of current. And so, and once you realize that if you make the hypothesis that you actually have this distribution in gap sizes, what you should be able to do is you should be able to synthesize oligomers of different length, mix them back together, and that should improve your yield. And sure enough, we find that about 1 in 5 of the devices works with when we adjust the molecular lengths to match the lithographic distribution and sizes that we have. And these cobalt terpyridyl complexes behave similarly to the ones that I described earlier. So how many molecules can actually bridge the ends of these? Well, this is obviously not reality. This is just a cartoon, but this is a 6,6 carbon nanotube, and this is the molecule that I showed, the first one that Jennifer Claire had synthesized that we used to optimize this process around. So it's an unusual case because actually in this case the leads are actually thinner than the molecule is, so the molecule is actually wider. And this is also not reality because the cut that we've taken out of the carbon nanotubes is completely vertical. And so this probably also, these cuts are probably jagged, and that's also going to lower the number of molecules that could bridge the ends of these. So you can imagine possibly a second one here, maybe a third one here. And with some photoswitchable molecules and some large diameter tubes, we've seen evidence that we've had a couple, 2 to 3 molecules in one of these gaps. But the number of molecules, and it wasn't worth fighting the reviewer over this, the number of molecules that can bridge is a small number. And it depends on the size of this molecule and the diameter of the tube. But what you might say, if you were a critic or a skeptic, you might say that what you did was you took carbon nanotubes, they're ballistic conductors. You went in and did all of this stuff to cut them and reconnect them with these molecular wires, and you made them not such good conductors. And that doesn't sound like a particularly good research program. And I think the answer to that would be that you really need this bridge to do something other than just carry current. So we wanted to show that we could write information into this molecular structure that allowed it to do something other than just carry current. So we took these oligoanilins, and polyaniline in bulk is known to switch its conductance with pH. And what we found was that we could reconnect these devices, and then as we switched from pH 3 to pH 11, what we saw is about an order of magnitude change in the conductance in these devices. I'm not going to take you through the control experiments, but suffice it to say that the switching occurs because of these oligoaniline devices. And it provides a molecular signature that the molecules are able to do something if you write the right information into them. And if you think about, one of the things that fell out of this work naturally, and I'm skipping now forward several years, was that if you think about DNA and the work that's gone on over the last few years about conductance through DNA, the size of the DNA double helix is about the same size as the diameter of the carbon nanotubes. And so we wondered if it was possible to begin wiring up DNA using these carbon nanotubes as electrodes, just given this nice size complementarity. And it gives us access then to things that have a lot more information programmed into them. And so we worked with Jackie Barton's lab, and they would send us DNA oligos that had been tagged at the end with amines. And we focused initially, I'm skipping a lot of experiments here, but we focused initially on single-stranded DNA that had amines on either end. The reason we did was because that, for us, provided a more interesting platform, because now you have a second strand that's non-covalently associated. You could imagine binding to both ends of the double helix, but we've done both of these. These turn out to be sort of a dead-end street in our hands, and this looks like, for us, is a more interesting structure. So you can cut these, you can reconnect them with DNA, and you see things that look similar to what we saw previously for the molecules. And if you estimate what the conductance of these devices is, it's similar to what you would estimate through the basal plane of HOPG based on work from Millie Dresselhaus at MIT. It's within an order of magnitude, which is comforting because you have this pi stack that you're going through in this case, as you do in this case. And then we asked the question, if the DNA is actually supporting the conduction, we should be able to take a restriction enzyme and go in and cut the DNA, and we should see that the device goes from an on state to an off state. And that's exactly what we see shown in this curve here, showing the current that basically goes down again to the floor. We did a control experiment that lacks the sequence for the restriction enzyme, and you basically see no measurable difference between the two before and after you treat it with the restriction enzyme. So the DNA at least is close enough to its native conformation that the enzyme is able to act on it. We also did a series of experiments now because this second strand is non-covalently associated. We can float that strand off, we can put in a mismatch strand, and we can ask the question how much that affects the current in these devices. And this shows the IV curves going from well-matched to CA mismatch to GT mismatch. This just shows the current as a function of the strand mismatch on the same device, gone from well-matched, CA, GT, well-matched. And you can see that the current drops off, comes back up, and then it drops off again. And so you can actually measure with, on the order of about a factor of 200 decrease in the current in these devices, a single base mismatch in a 15 mer of DNA. And that, that's sort of a hammer that's looking for a nail. If you think about this this idea that when you pull one of these bases out or you really disrupt this packing, that you're going to get this large decrease, and that got us to thinking about, primarily motivated by discussions with Professor Barton at Caltech, we decided to look at proteins that would go in and bind to DNA that we had bridged the ends of carbon nanotubes. And with this methylating cofactor, they flip out a base out of this DNA double helix, and we should be able to see that as well. And so we focused on this methyltransferase that was recommended by the Barton group, that plus the cofactor, which is called SAM here. And to establish a baseline, we'll put in bovine serum albumin, and then you're looking at the current as you go from just putting in the enzyme plus the cofactor, and you see that once you've gone through both of these steps where you presumably flipped out the base, you're down now, you're very low in current, and then you can wash that complex off, and you can get back once the base is returned, been methylated and returned into the DNA double helix. You return to current levels that were similar to what you started with. What that means also, if this really is a single molecule device, it's now methylated. The only site that we had in that DNA sequence, it's now been methylated. It shouldn't be able to methylate a second time. So if you go through the series again with exactly the same device, what you find is that it's inert to methylation. And so the site has now been blocked because this is something that's unusual because it's a single molecule device, not an ensemble. You can also program in multiple sites, and you can see the same sort of behavior. If you put in something that doesn't have the right sequence, you don't see any of this type of methylation. And so this is a platform by which you can actually connect molecules and biomolecules and measure the current that goes through them very easily on very short length scales, and it operates on the order of a single molecule. And I skipped over a lot of details, but we've connected molecular wires. We've connected these ones I talked about that were pH sensitive. Metal ion recognition, we've put in photo switches, these DNA mismatches, and we've also put in ligands for proteins, and when the ligand binds a protein, we see a change in the current in the device. And so this, I think, is a very nice platform for doing nearly one or few molecule electronic measurements. And it's a good way of transducing chemical and biochemical information into electrical signals. And what I said at the start was I was going to close with a do you know how much time I have, Matt? 2 or 3 minutes. Okay, so this will be quite a quick trip through the last half of my talk. So, this the idea here was to try to develop methods in which you could actually where you could actually, in a sort of high throughput sense, you could get a lot of data. You could collect thousands of single molecule conductance traces, and then you could look at the histograms to see what type of chemistry would be good at the contacts. And this is based on an experiment that was done at Arizona State by Nongjin Tao's group, and then a person who was a staff scientist in our nano center who was then hired in applied physics, Latha Venkataraman. This has been done jointly in her lab and my lab over the last few years. Basically, the way the experiment works is it's like a little tiny sewing machine where you have a gold substrate and a gold tip, and you push the gold substrate into the gold tip and you pull it back. And as the gold wire is formed when you press the tip into the substrate. And as you pull back, you can break this gold wire. And at a particular point, when you break it, you have 2 gold atoms that are pointing at each other. And that's the point where we wanted to try to do chemistry in these types of gaps. You can convince yourself that you have 2 gold atoms pointing at each other by looking at the conductance histograms for 2 point contacts pointing at each other, where you see it goes from the fundamental quantum of conductance down to just tunneling current as you break this wire. And you can do this in solvent, and that immediately led us to think, well, let's try to put molecules in there and see if we can bridge the ends of these 2 gold atoms. And it turns out the 2 most common end groups for molecular electronics are thiols and isonitriles. This shows the individual traces, a selection of the individual traces from this breaking experiment. And basically, for the thiols and the isonitriles, there's no plateau like you saw in the gold chain alone, or for these molecules, which I'll show you the structure of in a minute. For the thiols and the isonitriles, these conductance, when you break this wire, they have this very broad, sort of featureless type of structure. And what we found almost by accident was that if we actually use 2 electron donors like amines rather than thiols or isonitriles, we could get sharp plateaus in these breaking events. If you sum all those up and make histograms, this shows the counts, and these are over many thousands of experiments. Using the same color coding, this is for the amines. You see a nice sharp peak in the conductance histogram. For the gold line, which is the gold wire, you don't see any peaks, except out here at the fundamental quantum of conductance. And then for the thiols and the isonitriles, you see that they're also quite broad. This turned out to be a boon for us because it meant that we could actually do things like vary the dihedral angle between a biphenyl, and we could actually show that the conductance changed as a function of the cosine squared of that angle, which is what you would predict. We could also take other molecules that were 2-electron donors, like amines, methyl sulfides, and dimethylphosphines, and we could actually see very nice sharp conductance histograms, and we could actually vary the number of methylenes that intervene, get decay constants out of this, and these were consistent with other decay constants in the literature. These methyl sulfides, this bond here is free to rotate, and what we found was that if we actually tied this back to constrict the angle that that lone pair, which is binding to the gold, can make with respect to the pi system, we could actually get much sharper histograms. And so these types of locked systems turn out to be quite nice. I'm going to skip to the end. Basically, we made some very long molecular wires. These are oligomers of polyacetylene. We have phenyl groups on the end of these, and we would put these binding groups, and we would go in and try to measure their conductance. These molecules, as you would predict, as you make them longer, their color goes further out into the red because you're lengthening this path of conjugation. And this is, I think, at this point, is sort of a nuance, but the long and short of it is you can lower the homo-lumo gap in these molecules by making them longer. Then we would take these to Latha's setup, and we would try to do these single molecule measurements, and we could get relatively sharp conductance histograms out of these. And just like we would predict, these ones that have the locked sulfides actually gave us sharper histograms than the ones that were unlocked. We could actually look at this as a function of the number of CC double bonds that we had attached between these two phenyl groups. We could extract out a decay constant, just like we did with the alkyl groups. And what we find is a decay constant of 0.22 per angstrom. And that number turns out to be important for the last thing that I'm going to tell you in just a minute. If the story stopped here, it would be relatively unsatisfying, because what I told you is we made some molecular wires. Their homo-lumo gap shifted as we made them longer, and then we could connect them and get a decay constant out. And that's kind of a wheels around sort of project. But we actually found that something that was actually quite interesting is in the histograms of these molecules, as they got longer, we see two, if you log bin the histograms, you can accentuate this, but you see two peaks for the longer molecules in the conductance histograms. And this stumped us for about 9 months as to what the origin of these two peaks were, because you should only see one peak. And you can actually make two-dimensional histograms, and so the intensity is coming out of the screen at you, and this is showing displacement in angstroms. And so you're able to pull these junctions, and as you pull them for the longer molecules, what you find is that there's a valley. There's a low conductance peak, a valley, and then there's a high conductance peak, a valley, and then a low conductance peak. And this got us to, we did a number of control experiments. These nitriles were installed for synthetic ease, but it turns out if you leave the nitriles off, it works even better. If you leave one of the methyl sulfides off, what you find is that you actually still see a peak in the conductance histogram. And this got us to wondering, well, maybe these electrodes and these undercoordinated gold atoms are able to bind along the oligoene chain. So Mike Steigerwald, who works with me, did some relatively simple calculations where he just took a gold 2 cluster, if you will, and he bound it to the methyl sulfide, and he asked the question, where's the density along the chain? And this is looking at the HOMO, and you see that it's all along the oligoene. It skips the phenyl, and then it's on the methyl sulfide. Same for the molecule that lacks the other methyl sulfide. And this got us to wondering if actually these electrodes were actually binding along the oligoene chain. And then as it reached, so you have a structural contact, and then you also have an electrical contact through the oligoene chain. And if that's true, what you should be able to do is trap the molecule and then move the piezo back and forth, and you should be able to you would move the electrode along the molecule, and you should see a change in the conductance, which is shown here in this histogram. So basically, you can trap the molecule, and it's like tuning a guitar string. You're moving these two electrodes back and forth along this molecule, and you're tuning the conductance. And it turns out the kicker is that the decay constant for that is the same as the decay constant we measured for the different links of these oligoenes. And so to us, this looks like the single molecule equivalent of a resistive potentiometer that you can actually tune by tuning the distance between the electrodes. And it also points to a new way of thinking about designing electrical materials in the context of these types of devices, where you have both a structural and electrical contact, and they don't necessarily have to be the same. And I think you might argue that there's some benefit in them not being the same. So just to summarize, because I think I've used up all of my time, I talked about two different systems to try to look at single or few molecule devices. One where we cut carbon nanotubes, another where we dynamically break gold wires in solution, and trying to look at how we can incorporate reaction chemistry and molecular design into these types of devices. I tried to acknowledge the students that helped along the way, and these are the foundations and agencies that have funded this work, and I'd like to again thank the Dreyfus Foundation for their support and also for the invitation to be here.
Thank you, Colin. Okay. Questions, comments?
That was very good. Have you considered using this as a photon detector by looking at conductance changes for infrared, visible, and so on?
Well, the closest thing we've done to that is we've looked at these photoswitchable molecules that switch from a non-conjugated to a conjugated state. As is most things in chemistry, it's a little bit easier said than done. It turns out once it becomes conjugated, then what we find is that it's very difficult to get the molecules to revert to the open state because they're basically they're conjugated into these long leads. So we had to design it in such a way that we actually don't see a photo-reversible switch. We actually have a thermal cycle that opens it back up. We use paroles instead of thiophene in those devices. But the exact answer to your question, we haven't looked at exactly what you were asking about, no.
I might be next. Hi, Colin, over here.
Hi.
It's terrific stuff. I had a question that really follows an analogy of the single molecule fluorescence studies where the fluors can blink between on and off states, presumably because of conformational changes. Do you see any of that with an intact wire that over time it can blink or switch between its states?
Yeah, so the measurements I was showing here weren't actually done in real time, but we have a setup now with a microfluidic platform, and the actual single molecule device is a little bit different, but it's more or less you're looking at a conductance change. And there we can actually, if we put a DNA, if we have a DNA double helix that's close to its melting transition, we can actually see it hybridize and dehybridize, and we see two states for that. And we actually use the FRET software to actually go in and process the data. It's just that I was tempted to talk about that today, and I just didn't get enough time to put it together in this talk. But yeah, the answer is sort of not in this exact system, but in others.
Abe Strook from Cornell. Can you make sense of the response to the gate voltage? It seemed like there was a large diversity of behavior with the gate voltage, and in particular for the DNA. Is that
well, so there's, I mean, one of the big problems that we spent a lot of time working on over the last few years is we'd like to be able to actually have the same carbon nanotube every time when we do these experiments. And the reason is because you have a large diversity to start off with, and then you can also imagine that you may have a bundle of a couple of carbon nanotubes and things like that. And so the response to the only thing that is consistent across each of the devices is that the only thing we're modulating with the gate is actually the carbon nanotubes, because these are very thick oxides, and the devices are very large. To really get a response of the molecule to the gate, we have to put a local gate with a thin oxide and all of that. And these devices were made in a very easy and straightforward way where we grow carbon nanotubes by CVD and just adjust their density to where they're spread out over the substrate. Then use a TEM grid as a stencil to where we can actually then just attach these metal pads. So there's only one lithographic step, which is that one E-beam step, which is painful. But other than that, it's like spam from the can. So we're now going back and we're redefining this to where we're actually taking sorted carbon nanotubes that you can nowadays purchase that are all the same, cutting them down to length, connecting them in solution and depositing those. And that should get around this issue of the variance from device to device.
In the case where you
You're not going to ask the
trap...
VC. You're not going to ask the VC question, are you?
No. In the case where you trap your molecules between your gold atoms, is that random trapping, or can you control where along the chain you trap?
Well, so I mean, it's not random in the sense that you're breaking the wire and you have control over how far you've moved one electrode with respect to the other. But there is an issue when you pull that. Sometimes when it breaks, you will see some snapback, and you don't see any tunneling if there's no molecules there. You see no tunneling conductance. It just goes from 1 G0 down to basically nothing. And then other times you'll see that it sort of goes through a tunneling regime. And so you can control it in that sense. And the yield for trapping a molecule in many cases, and in particular for these very long molecules, the yield is very high. And once it was trapped there, then we just vary the height via the piezo, and you can move it up and down the chain essentially at will.
Hi, Seogui Jang from Queen's College. I have two questions, so you can answer in the order you like.
Thank
you. The first one is, in your last molecular system, you said that there are two different states of conductance. It's because of the contact between the molecule and gold nano tip. But if that is the case, I don't understand why there are only two distinctive states. There may be multiple states.
Well, no, I want to. Maybe I was running out of. Mark told me I had about 40 minutes, so I was rushing at that point. There's two broad peaks separated by a valley. Right, and that valley is when the tip goes across the phenol, and you certainly do see many states as you access different points along that oligoene chain, and that's where you get this decay constant, because we vary it along the ene chain, and you see a decrease or increase in the current whether you're going closer or further apart.
So what is the temperature
Room temperature.
Room temperature. So if you lower the temperature, you may see many different.
Yeah, in this setup, we can't actually lower the temperature. I mean, it's one of those complications that the graduate students usually start speaking a different language when you ask them to now adjust this to a variable temperature experiment. But it's a good suggestion.
So the other question is, have you compared your experimental conductance data with theoretical calculations, for example, based on non-equilibrium green function calculations?
The easy answer is no, we haven't done that. But the closest thing we came were the calculations I showed, which they're not the type of calculations you're wanting to see. But I don't want to say anything in politics. So no, we haven't done it.
Pointed out to me that we have ample time for lunch, so even though I was we don't really have to.
Oh wait, I have the last third of my talk then.
Dmitry Talapian from University of Chicago. So your the conductance or conductivity of single molecule that you say is like very small fraction of quantum of conductance, about 1%. Where do you lose the rest? Is it injection of carriers to put carrier from electrode on the molecule, or is it like electron phonon scattering when it moves across the molecule? What?
Well, I mean, I don't think there's one answer to that, but one place where you lose a lot of it is at the contacts, because you have these contacts that are basically, in this case, I think are pretty resistive. But then in addition to that, you also have an issue with, you have to match the molecule to the electrode material, and those energy levels have to somehow be in registry with each other. And so, the molecule can also play a key role. And if you start thinking about, all right, well, I want to design a molecule where it's going to line up well with the electrodes, you then also have this issue with the contacts that you have to deal with. And there's been some recent work that I can't really talk about, but where you can make contacts that are actually very transparent, and then you get things that are very highly conductive.
Thank you.
Thanks.